Now we have the next gen. We get to celebrate those with an accomplished career, and now we move on to the students who are competing in our poster competition. They get 1 minute to introduce themselves, engage you so much that you're going to stop by their posters or visit them online. A few of them are virtual, and we've already talked about that. So, nope, come on up, like line up in the order. Can you go to the next slide, please? Oh, nope, go back. This is the order we need to do it. If there's someone virtual in front of you, then line up behind the other people. We're going to go like this. You have a minute. While you're in line, set your watches, your phones to 1 minute, and be ready to introduce yourselves. And then we move on to the next one. Does that make sense? You guys are all getting yourselves organized. Did you guys hear me, or were you getting yourselves organized? Sorry, we were organized. Okay, you have 1 minute. Set your watch, your phone, and as soon as one person is done, just keep moving. I'm not going to come back up. Okay. All right. Good luck. Have fun.
All right. Hi, everyone. My name is Sophia Vlahakis. I am a rising fifth-year graduate student at MIT. I work with Professor Carrie Cahoy in Star Lab, and I've been recently collaborating with Professor Tansu Dalen here at WashU. My poster is on a mission concept that we're proposing to do follow-up observations and characterizations of near-Earth objects. And this will be a small to medium-sized satellite with an optical telescope in geosynchronous orbit. The main motivation for this is to, for planetary science and planetary defense purposes, to do follow-up observations on the many, many new near-Earth objects that we're expecting to find with LSST and NeoSurveyor. Thanks.
Hello, I'm Cameron Kelly. I'm a graduate student from the University of Central Florida. My poster is on retrieving particle size distributions from laser propagation decay. When landers approach the moon's surface, it creates a plume of dust that can damage nearby assets, and this damage can be mitigated by knowing the particle size distribution of the particles. So the motivation behind Project Ejecta Blast, which is the project that my research is a part of, is to create a lander-mounted instrument that can retrieve the particle size distribution. And this is done by recording a set of decay constants that describe how the intensity of the light decays. And what my research focuses on is using the set decay constants as well as different methods of inverting integral equations to approximate the particle size distribution. And we expect that the mathematical methods made in this project will be very helpful in future lander projects. Thank you.
Hello, everyone. My name is Romain Fontaine. Before coming to America, I was working on Martian rovers at the European Space Agency. But then, thanks to the Artemis program, my interest shifted to lunar space exploration. And this led me to start my PhD program at Georgia Tech, focusing on dust mitigation, which is one of the biggest challenges since the Apollo era. You may know that the electrodynamic dust shield, which uses electrodes, is one of the most promising solutions against dust. But we still don't really understand the system, and we really don't know about its efficacy on the lunar surface. This is why at Georgia Tech, we've been tackling these issues through high vacuum experiments, coupled with numerical modeling to better understand the system's design space, but also optimize its performances for the moon. We've had interesting results so far, which will be presented tomorrow at the poster session. And this is why I'm inviting you all at poster number 9 in discussing one of the greatest challenges of space exploration and lunar exploration, that is dust mitigation. Thank you very much.
Good afternoon, everyone. My name is David Sanchez Valencia. I am an undergrad studying astrophysics at the University of Central Florida. I work with Exolith, run by Dr. Dan Britt, and I'm here to present my experiment. So we have to learn from the past, we have to live in the present, and we have to understand how the future is going to unfold. So our experiment and the purpose of it is to finding lunar landing locations in which can withstand the forces and the weight in the future of our future spacecraft, as well as mitigating rocket exhaust effects, and finally building infrastructure. Now we're doing this by evaluating how bulk density affects cohesion and the linear density friction. Now we do this by evaluating some regolith with two of them. We do these experiments by atmosphere and we do it by vacuum. I would love and would invite you to go to my poster upstairs so you can see the key findings and how we mitigate the effects of outgassing from these effects. Now, I really think and I really believe that in order to before we start exploring more of the stars, we have to understand the soils and the grounds in which we stand. And that's why we study regolith. Thank you.
Good afternoon, everyone. My name is Ethan Ayari. I'm a third-year physics PhD student at CU Boulder, working under Professor Mihai Haranyi, who briefly advertised this poster during his talk earlier. If you stop by my poster, I'm going to pitch you an instrument for your lunar orbiter mission. This is a dust mass spectrometer that for each dust particle it encounters, it can report the mass, velocity, and isotopic composition. The moon, like other airless bodies in the solar system, is continuously bombarded by micrometeoroids from all directions. These result in ejecta plumes of dust that this instrument would fly through and characterize. The permanently shadowed regions, as the name suggests, are unadulterated by the solar wind and radiation, and so they're thought to contain volatiles such as water. To this end, at our dust accelerator facility at CU, we calibrated this instrument with a hydrated mineral at flyby speeds typical for such a lunar mission. And we were able to detect how much water was in the sample. So this is ready to go, and I'd love to tell you more about it at my poster.
Hello, my name is Elena Dolgus. I'm working with Dr. Addie Dove at the University of Central Florida. As part of the upcoming CLIPS mission Lunar Vice, I am interested in the geotechnical properties of the regolith. So this includes the albedo porosity relationship. To look at the albedo, I'm using previous mission datasets, such as the LRO mission and its instruments LAMP and the camera's LROC. So I have already looked at these albedo relationships from orbital imagery, but in order to look at porosity, I'm diving a little bit further into that with things such as Hepke parameters. There is other work that I plan to do as this is still ongoing in preparation for the mission. So if you'd like to learn more, I am poster 12 and we can talk about it more. Thank you.
Hello, my name is Matthew Hernandez. Today I'm talking about I'm an undergraduate from the University of Central Florida working for under Dr. Kiri Donaldson Hanna. And so my poster is about the visible to near infrared spectral effects of porosity and albedo on different asteroid and lunar analog samples. And so in our study, we used the visible to near infrared range to collect spectra simulants that we created. And these simulants were of two different particle size fractions and at specific ratios of olivine, potassium bromide, and carbon black. And the purpose of these ratios was to achieve different albedo values to similar ones you would find on the moon. And so in my poster, I made various plots to show the spectral contrast, highlighting the absorption feature around 1 micron. The results from this show that as you add more carbon, potassium bromide to the simulants, the spectral features becomes more linear. So in the future, we hope to examine these analog samples in the mid to infrared range, and I hope you guys can come look at my poster. Thank you.
Hello, my name is Jacqueline Vasquez, but you can call me Jackie. I am an undergrad at Boston University, and for the past year, I've been working on a project that primarily focuses on trying to gain an understanding of the moon's magnetosphere during early epoch. So for the past year, we've been developing 10-moment multi-fluid models that depict the moon with a 2D dipole. We are particularly interested in trying to see what understanding this period of like lunar magnetic activity can tell us about current features that we see on the moon, such as lunar water ice in the polar regions. So if you're interested in this and want to come see my models, also because we just recently started working on refining our 3D models. So if you think this is cool and you want to see my models, please come talk to me tomorrow.
Hi, everyone. Hopefully you can hear me. My name is Talia Nelson, and I'm an undergraduate student at the University of Michigan in Ann Arbor. I'm the research team lead of a student organization there called the Collaborative Lab for Advancing Work in Space, or CLAWS. And every year we participate in the NASA Suits Challenge, where we are tasked with designing user interface solutions on augmented reality devices for future spaceflight needs, such as maintaining a human presence on the moon and ultimately Mars. My sub-team works in support of this main challenge, and we've designed and carried out an experiment to test the limits of an augmented reality device called the Microsoft HoloLens in a simulated Martian lighting environment. We've collected data from human participants in response to contrast sensitivity and visual acuity tests we've designed on this device. We hope that our study, along with future research into this topic, can help provide informed design recommendations for future technology. I look forward to speaking with you all during the poster session, and thank you for your time.
All right. Hi, everyone. My name's Jared. I'm a PhD student at the University of Central Florida. And my poster details some work I did as part of a visiting technologist experience under Dr. Bob Anderson at JPL. Specifically, I worked on the SPARTA project. SPARTA is a low mass, low power, shallow subsurface regolith characterization probe that combines a cone penetrometer, vein shear tester, thermal conductivity probe, and dielectric spectrometer all into one instrument. SPARTA can inform on critical properties of the regolith at unprecedented spatial resolution, though, of course, these measurements don't mean much without proper quantification and analysis, which is exactly what my poster goes over, the development and validation of a data analysis software suite, specifically for use for SPARTA's lab, field, and eventual planetary flight data analysis. It's based on ASTM and other well-established standards. I won't give more details away here, so come see my poster, and I hope to see you there. Sorry I couldn't be there in person.
Hello, everyone. My name is Jacob Giles, and I'm a master's student at the University of Maryland. My poster focuses on the challenges of near-surface seismic imaging using traditional surface wave methods and the possibility of using more complex full waveform inversion methods to try and overcome these challenges, with the goal of interrogating the complex near-surface structure analogous to the lunar near surface. Our study takes place around Espy Crater in the San Francisco volcanic field, which shares many geometric similarities with the lunar surface, making it an optimal lunar analog site. The seismic data can aid in the understanding of the formation of planetary structures from the near surface to the deep interior, and will broaden our capabilities as we make our way back to the moon. Thank you for your time, and I look forward to speaking with you all more at poster number 44. Thank you.
Hello, my name is Miriam Heron, and I'm starting my sophomore year at the University of Rochester this August. I'm working in the lab of Professor Dustin Trail, and we're investigating the OH concentration of Apollo 14 zircons. Our main goals for the project are to gain a better understanding of the composition of the lunar crust, as well as the volatile history of the moon in regards to water. We are working under the assumption that amorphous zircons will not record a primary water signature, by which I mean water incorporated into the crystal at its formation. And so our first step of the project was to determine the crystallinity of the grains via Raman spectroscopy. We took over 200 measurements, which show our grains to be characteristic of crystalline zircon. We then turned to catholuminescence imaging to search for chemical zoning, and we began EBSD analysis, or electron backscatter diffraction, to look for impact microstructures and to determine the lattice orientation of each grain, which will be crucial when we arrive at the final step of our project, FTIR spectroscopy, to actually investigate the OH concentration of each grain. My poster is upstairs. It's purple. Please come by and ask me questions.
Hello, everybody. My name is Aaron Kessler. I work at the Impact Lab in Boulder, Colorado. At the Impact Lab, we have a Pelletron dust accelerator. And previously, in order to access the data from the accelerator, the researchers would have to use SQL queries or a single instance LabVIEW software. And this was a very inefficient and restrictive way to access and visualize the data. To solve this problem, I have developed a new software. It is a remotely accessible, secure web application. And this application has intuitive tools for querying, plotting, and downloading the data. This enables the researchers to access and visualize the data far more efficiently than they were able to previously. So if you're interested in learning more about the software Or if you're interested in having a similar software implemented for your research, please come see me at my poster tomorrow. Thank you.
Hello everyone, my name is Ari Mehta and I'm a student at Belleville High School in Wisconsin. My classmate Aiden and I recently participated in the XMS program and we decided to research the lunar surface, how it's been affected by impact cratering over time. Specifically, we compiled data on the frequencies of impacts across varying lunar regions. We then use this data to compare relative ages of these regions and to draw conclusions about why they might be different. Thank you.
Okay, so hi, my name is Arjun, and I'm here with the Logos Charter School XMAS team. Our project this year was to train a machine learning program to identify sinuous rills, craters, and pits on the moon. Last year, the team tried to manually find undiscovered sinuous rill candidates, but this process was tedious. This year, by accessing images of sinuous rill regions from the NAC image database, we were able to create a dataset capable of training the program to identify the features mentioned earlier. In order to prepare the data, we first accessed images of 100 different rills on the moon and annotated the regions with rills and craters using an annotator tool. NASA scientists who developed the device used the prepared data to determine the capability and performance of the program. We plan on continuing this front-of-the-line research as its capabilities are limitless and could lead to a lot more discoveries. Find us at Poster 2 to learn more about our project. Thank you for listening.
Okay, well, thank you all. You all did very well. And thank you to the judges that are hidden in the room and watching. We're very excited about these competitions and the opportunity for you to meet all of the students. There's a very high percentage of students here this week. And so we really encourage everyone to talk and network.